So for this tutorial, I'd like to take a look at calculations, how we do math operations, and also how we can do different logical operations as well. Now before we get into actual new instructions, I'd like to take a look at what the problem is going to be for today with the example code. So if you remember in the previous example, we got the starship moving around on the field with key presses. It was a little sluggish, however, and so I'd like to have two things here. First of all, I'd like to be able to move the ship faster than just 1 pixel per tick, which means that I need to be able to do something more than just incrementing or decrementing by 1 the position, the coordinate of the ship. And the second, I'd like to switch to the joystick for the input, not using the keyboard. And if we take a look at how the C256 joystick port works, which is fairly similar to on computers like the Commodore 64 and the Atari, you have a single byte register for the joystick. You can see the one for the C256 down below, where each bit represents whether or not a particular button or switch is pressed or closed. So there's a button for the joystick is moved into the up position, there's a bit for it's moved into the down position, left and right, and then there is a bit for each fire button that the joystick might have. And in the case of the C256, it supports 3. So when you're wanting to figure out which way to move the ship, you have to be able to look at a particular bit in that port and say whether or not that's turned on. So the actual number that you see in the port is maybe not nearly as interesting as that individual bit. And the other thing I should indicate with the C256 is that by default, these bits are all 1, and they are only moved to 0 if the button is pressed or the switch is closed on the joystick. So what instructions do we have on the 65816 to do math? There are really 2, or at least 2 main ones. One for adding 2 numbers together and one for subtracting 2 numbers. And the addition one is ADC, which stands for add with carry. And all it really does is it takes the value that's in the operand and it adds it to the value that's in the accumulator, and that added value goes into the accumulator. Now, I mentioned that it's got with carry in the name. And if you remember from your early days of doing math in elementary school, you probably remember doing longhand addition and how when you'd add 2 numbers up together in a column, you might have to carry the 1. Well, that's what this carry thing is. The ADC instruction is set up so that you can use it in a chain of additions so that you can add really any 2 numbers of any size you want together by simply chaining these adds together, because it uses the carry bit in the processor status register to indicate whether or not a carry is needed for the addition. So you see I've got a little diagram here on the right hand side with ADC in the middle. You've got the accumulator coming in as 1 number to be added, the operand coming in as the second number to be added, and the result's going to go into A. But the carry bit is being consulted, and if the carry bit is a 1, ADC will add 1 to the value in the accumulator and the operand. In other words, it's going to carry a 1 into the addition. And then if the result of adding an operand and that carry bit is larger than can fit back into the accumulator, if in other words it needs to carry a 1 out of that addition, then the carry bit coming out of the out of the adder is set to 1. And if no carry is needed, then it's set to 0. So if you need to be adding together, say, 32 bits, you could do 2 16-bit additions with ADC, and the carry from the lower 16-bit addition is then added into the upper 16-bit addition if you do them in the right order. SBC works in a very analogous way to do subtraction. It simply subtracts the operand from the accumulator, but in this case it's using C as a borrow bit to indicate if you need to borrow a 1 as it were for a previous addition. And the borrow is indicated by the carry bit being 0. So if the carry bit is clear, then SBC will subtract an additional 1 from the result before it puts it in the accumulator. And if the result of the subtraction would require a borrow when you're doing it in longhand, then it will set the carry bit to 0 at the end of the subtraction. Otherwise, it will set it to 1. Now, as you might imagine, this means that it's pretty important that your carry bit be in a known state when you're doing either an addition or subtraction on its own of just an 8-bit or 16-bit value, or if you're doing the low order bits of an addition or subtraction first before you do the upper order bits. So in the case of adding, you probably want to clear the carry bit before you start the addition. Now, you could use the rep instruction that we talked about before, but there is a simpler single byte instruction called CLC that clears the carry bit. Likewise, when you're doing subtraction, you probably, generally speaking, want to set the carry bit before you do the subtraction on a single subtraction or the first low order bits of a subtraction of a larger set. And again, here you could use the SEP instruction, but there's also an SEC instruction that will just set the carry bit. And both clear carry, CLC, and set carry, SEC, are single byte instructions. Most of the bits in the processor status register have a set and clear instruction that go along with them. So that covers the basics of arithmetic, but we also need to be able to talk about individual bits. You're treating a byte or word not as a number, but as a collection of bits. And that means we need to be able to do some logic on the individual bits, or what's called bitwise logic. And we have 3 instructions that are in the 65-bit16 that will help us here. And these really implement Boolean logic or Boolean algebra, if you've ever worked with that before. These operations exist in most programming languages. In C, for instance, there's the AND, the ampersand operator, the vertical bar operator, and so on. And the 3 instructions we have here are AND, OR, and EOR. So the first one here that I'll look at is bitwise AND. And all it's really doing is, for every bit in the accumulator, it looks at the corresponding bit in the operand. And if both the accumulator and the operand bit are set to 1, then the resulting bit in the accumulator as the result will be 1 as well. If either of them is 0, then that resulting bit is 0. Now I've represented that here with this diagram where you can see I've got the accumulator bits at the top, I've got the operand bits down below it, and each bit, so on the left we've got bit 7 of the accumulator and bit 7 of the operand. That's a 1 and a 0 respectively. The ANDing of that, because only one of them is 1, the ANDing of that is 0, so that 0 is what's going to go in the 7-bit of the accumulator at the end of the instruction. The next bit over, bit 6, we see that both the accumulator and the operand have a 1, so the AND of that is going to be 1, and that's what's going to go into the accumulator's 6-bit for the result. And you can see each individual bit is calculated in the same way. You can see also that the bits are calculated independently. The result in bit 7 does not depend on the values in bit 6 or bit 5 or anything like that. And that's why these are bitwise operations. The next of these instructions is OR, which stands for the logical OR of the accumulator with the operand. So this is doing very much the same thing that AND is doing, except that the resulting bit is going to be a 1 if either or both of the source bits are 1. So in our example here, we can see that bit 7, the accumulator is set, the operand bit 7 is 0, but because the accumulator bit is 1, then the resulting bit is going to be a 1. But over in the far right, we see that 0 is in the accumulator and 0 is in the operand, so the result on that one is 0. And finally, we have EOR, which stands for exclusive OR. I believe in C that's represented by a caret operator or a circumflex operator. EOR is kind of similar to OR-A, except that whereas OR-A, the result will be a 1 if both of the inputs have a 1. In the case of EOR, it's only true if one or the other is true. If both are set to 1, the result is going to be a 0. So again, you can see here, bit 7, accumulator 7 is a 1, operand 7 is a 0. So only 1 is true. That means the result is going to be 1. Bit 6, the accumulator and the operand both have a 1 in bit 6. And because they're both 1, exclusive OR means that the result is going to be a 0. And then likewise, if we go over to the very far right, we have accumulator and operand both having a 0 in there. So the exclusive OR of that is just 0. And when we get into the example code, we'll see how some of these instructions can be used. But in general, these can be very useful for looking at specific bits, filtering out clusters of bits for things. So we only look at this set of bits or that set of bits, or for flipping bit values and that sort of thing. So now that we've looked at a couple of new instructions, I'd like to add in a new addressing mode, in particular direct addressing. And this is a pretty important addressing mode because it's the basis of some of the most powerful addressing mode features in the 65816. It looks an awful lot like absolute addressing or like absolute long addressing. But whereas absolute long can address any memory location whatsoever, and absolute addressing can address any memory location within the current data bank, direct addressing only works with a small window of 256 bytes that exists within bank 0. And that window, while you can move it, its location is indicated by the DP register, the direct page register, which we've been ignoring up until this point. And the way this addressing mode works is that the instruction will take a single operand byte, and that byte in the operand is added to the value in the direct page register to get the address of the location that your instruction wants to use. Now, why is this interesting? Well, one of the reasons is that direct instructions are very fast, and they're also short in that the instructions are just 2 bytes. But direct addressing instructions are typically the fastest of the instructions operating on memory locations on the chip. If you're familiar with the 6502, direct page is really an extension of the 0-page mode that you may be familiar with, and it replaces it. So all of the instructions that were 0-page instructions are on the 65816 direct instructions. And this little diagram down here is showing you how that direct addressing mode works. On the 64 tasks, the little assembler hint to tell the assembler that you want to be using direct addressing is @B, which means that you have a single byte for your operand. So load A @B5 is saying that you want 5 as the offset for direct addressing. And so what you get is in the instruction is A5, which is load A direct, 05 being the address there. That is then added to the value in direct page, and that gets you 010A as your effective address, which has, in our case here, a 56 in there, and so that's the value that gets loaded into the accumulator. You may notice that I've got a full 24 bits written down in the DP register, but the upper byte is grayed out. That is because the direct page register is actually a 16-bit register. But because it's always referencing memory in bank 0, the upper byte or the bank number is set to 0. It's implied 0. So I've written it there just to make it clear that we're addressing bank 0, but you don't actually get to change that. You don't get to change the bank here. I need to interrupt myself here and correct an error on the slide. I have as my assembler syntax here LDA at B of 5. Now, you wouldn't actually provide the offset of 5 here like this. Instead, what you would do is either provide a label after the at B for the address you're trying to access, or you might put in the actual address, so LDA at B of $10A, in this case. And then you would let the assembler calculate that offset. It's kind of like with branch, BEQ, for instance, where you don't put the offset in yourself, you let the assembler compute it. There is a syntax for the direct page modes in 64 tasks where you can put the offset in yourself. And that's kind of what I was thinking about here, which is why I got confused. But anyway, I wanted to correct this here. Just so you know, this isn't exactly how you type it. You'll see in the example code how you'd actually use this mode. So this is all very interesting, but we have to be able to set the direct page register to make this useful. And so that means we need some more instructions. And we have a couple here. We have 4. You can, as what you can with every other register in the chip, you can push it to the stack and pull it from the stack. So there are 2 instructions there for that. PHD pushes the direct page register to the stack. PLD pulls the direct page register from the stack. One thing that's important to note here is that the direct page register is always 16 bits. It doesn't matter if the accumulator is 8 bits or the index registers are 8 bits or if all of them are 8 bits. The direct page register is always 16 bits. So PHD and PLD will be pushing or pulling 16 bits to or from the stack. Unlike, say, PHA or PHX, which can work with either 8 or 16 bits depending on the size of the register. Now, you can push and pull D, that's very handy, but it's kind of slow as a means of setting the register, because I think PHD and PLD are maybe like 6 cycles long or something like that. But we have a couple of instructions that let us transfer values into or out of the direct page with the accumulator. So we have TCD that copies the accumulator to the direct page register, and TDC that copies the direct page register into the accumulator. Now, you might have noticed that it's referring to C and not A here, even though we're talking about the accumulator. That's potentially a little confusing, because it might seem like they're talking about the carry bit. Well, no, they're really talking about the accumulator, and they're using a nomenclature here where when you are dealing with a 16-bit accumulator, because again, the direct page register is 16 bits wide, so your accumulator has to be 16 bits wide for this as well. But when they're talking about a 16-bit accumulator on a 65x16, they call that C. The lower 8 bits of the accumulator is called A, the upper 8 bits of the accumulator is called B, and the total 16-bit accumulator is called C. So when you're doing this, when you're transferring C to D or transferring D to C, you will want to make sure that your accumulator is 16 bits wide before you work with that. And we'll see an example of this in the example code. All right, now let's take a look at the actual example code that I've worked up here for lesson 4. This is going to be very similar to lesson 3's code, except that I made some changes to use this direct page mode and to work with the joystick. So the first change here is I've defined a new label to point to the port that contains the joystick values for the joystick 0. So on the C256, joystick 0, which is the leftmost joystick port on the machine, that's located here at AFE800. Next, I'm coming down here and I'm defining another label for a constant. This is what I'm calling velocity. This is the value that we're going to add or subtract from the x or y coordinate as we're moving the sprite. This will let us do larger jumps as we're moving the sprite, so it can move a little faster on the screen. And I've just picked 2 kind of arbitrarily just to show that we can do something more than increment or decrement by 1. Next up here, I have defined some bit mask values for the different positions that the joystick can be in. And these correspond to what I showed in that little chart earlier. Now comes one of the bigger changes. Because I want to use this direct addressing mode, I need to set up our direct page register. And the way I'm going to do it, if we come back up here again, we have these 2 variable locations that I set up early on, 200 and 2002. These are the x and y coordinates, 16-bit values for the sprite, for sprite 0. And they're down here in bank 0, so we can use the direct page register to access these more quickly. And we're going to be using them fairly frequently, so it probably makes sense to have them be accessed that way. So what I'm going to want to do is I'm going to want to set the direct page register point to this very first one here, to 0200. And that's what I'm going to do here. So first off, I set the accumulator to 16 bits, and I load it with the address of that first variable. Now, I can't recall if I've used this syntax before, but this less than and greater than sign is the way 64tasks lets you say that you're only going to take a 16-bit address, not the full 24-bit. So it says, I really only want the lower 16 bits of the address of SP0X, and that value I'm going to load into the accumulator. And once I've got that, then I use the TCD instruction to set the direct page to that address. So when this is done, the direct page address is going to be 2000. Now, just like with the widths of the accumulator and the index registers, the way you've got to set the assembler and tell the assembler what those values are, in a similar sort of way, it really needs to be informed about what the direct page register is set to at any given point in the program. This is because if you are being unclear or ambiguous about what addressing mode you're going to be using, it's going to try to make its best guess. And one of the things it's going to do is it's going to look and see, can this address be accessed through the direct page mode? And if it can, then it will use that. So it really needs to know what is the direct page value to see if a particular address is accessible through that. Also, it will verify that a particular address will work with the direct page mode. And we'll see that a little bit down below. So this assembly directive here, dpage, this is how you tell 64tasks what the direct page register is set to. Now, in general, I don't write this sort of thing all the time in my code. I have a macro that I can use for this to kind of automate it and make it a little bit cleaner to read. All right, so we go down, we clear the screen as before, we set up the color lookup tables, and we load the bitmap as before. All of this is the same, setting up the Wiki registers, setting up the sprite registers, and so on. But here's the first, the next block of change. I have switched the addressing mode on these 2 stores to the 2 variables to be direct page using this @b. It's not really necessary to have done that, but before they were using absolute long, and here I'm just using direct page. So that shaves off 2 bytes from each of those instructions and makes them a couple cycles faster. All right, so now we come down and we have our little input loop. I'm just going to skip over this part for the moment and look at how we actually process the joystick. So first of all, the joystick register is a single byte, so we want to make sure the accumulator is short as before. We load the value from the joystick register. And again, we're using long here because that's way up in bank AF, or it's way off in memory. We really have to use long for this. But we get that value, and then we want to see, first of all, if it's pointing up. So we AND whatever that value is in the joystick register, we AND that with joy up, which if I come back up here, joy up is 1. So we're looking at bit 0 there. And if the value is a 0, then the bit for the joystick up direction was 0. And that means that we moved the joystick in the up position. So remember on the C256, if the button is pressed or the joystick is in a particular position, the associated bit is going to be a 0. Its kind of resting state is all ones. So by ANDing that 1 bit, we have said we're ignoring all the other bits. We just are looking at bit 0. And if it's resting, bit 0 is going to be a 1. When we AND it with joy up, it's going to be a 1. And then the ANDing of that is going to be a 1, which means that the accumulator will not be 0. And so we would skip this jump and we go on to the next step of checking the down bit. But if it's a 0 in the joystick port, that means we are pointing up. We get a 0 here at this stage, and we would go branch off and we would go do the up operation. Likewise, we want to check down. We go back and get the joystick port value again. We check now this time the down bit, which is bit 1. And again, if it comes back as 0, we go and do down. Otherwise, we check left and right in the same manner. Now, you might look at this and see that there's a little bit of a trap here, and we're going to get into that a bit later in another tutorial. But the problem here is that we're checking the joystick port 4 times in this loop. And the joystick can change in the course of these four loads. We're not looking at it at exactly the same time in each of these load A's. We might want to be checking these bits from the original value. So we could save that joystick port value to another variable down there in direct page mode and check that. There are a couple of other little solutions that we can look into. For the purposes of today, that's going to be fine here. This is not going to be a real problem. But I just wanted to point out that this is not exactly the best code, but it will show you how AND is working. So now, how do our up and down and left and right operations look? So they're pretty similar from before. Again, I'm changing the addressing modes for when I'm reading and saving our coordinates to @B, so using the direct mode. But then the other thing I'm changing is, originally I would increment or decrement the coordinate based on whether you're moving up or down or left or right. This time, however, because we want to be moving by 2 positions, not 1, I'm using SBC and ADC. So you see here, I set the carry to indicate that I don't want to be doing a borrow on this. I don't want to be doing an additional subtraction by 1. And then I'm subtracting velocity from our y coordinate to do an up. And then again, I check the minimum value and all that stuff that we did before. For down, I do a similar sort of thing, except I'm clearing the carry bit and doing an ADC. So remember, a borrow, when you're doing a subtraction, a borrow is the carry bit being clear. So if the carry bit is clear before you do a subtraction, you're going to subtract an additional 1 from the accumulator before you set the value. So that's why we do a set here. That says that we don't want to be doing a borrow, that we want to be subtracting just velocity from the accumulator. Similarly, when we're doing an addition, the carry bit is a 1 if we're wanting to add an additional 1 to the value, and it's clear if we just want to add velocity to the accumulator. So the carry bit kind of has, in a sense, a different sense for those 2 operations. So yeah, so here to do down, we add velocity to y, and we save y back, and then we do our SP0 at to actually move the sprite. Left and right work the same, but we're just doing it against the x coordinate as opposed to the y. And again, to move left, we subtract velocity from x. Again, we're doing a SEC or set carry before we do subtractions. We are only subtracting velocity. And when we want to move right, we add velocity to the x value, being careful to do a clear carry first, so we just add velocity. And then down here at SP0 at, we are, the other change here is again, because we have the x and y position variables in that direct page window, we're using direct page mode here by doing @bs before we set the actual hardware control register in Vicky. Now I glossed over something. Let's come back to that here. At the very top of the input loop, I have this strange little construct here where I'm loading a value into x and I'm calling a subroutine called IloopMs. Now, if I were just to run that code without this in here, you actually wouldn't see any motion on the sprite because the joystick is so quick to read that so little has to happen that the ship would just go, zooming off, on one side of the screen to the other. So we need to add a little bit of a delay on each of these loops to kind of slow things down and to actually have the thing moving at a reasonable pace. So this IloopMs routine, I just have this down here at the bottom. This is a set of 3 routines here, starting with iloop here at the top, iloop1, or actually 4 routines, iloop1ms and IloopMs. What these do is just add in some delays. iloop just does a bunch of no ops before returning. iloop1 is just calling iloop a bunch of times. And iloop1ms and iloopms, those are calling that some set number of times. In this case, ms, we set in x how many times we want to call iloop1ms. So this just gives us a kind of programmable delay based on no ops. This is, again, not a great way of adding timing. It's a cheap and easy way of adding timing. In practice, when you're writing an actual game, you're probably going to want to use the built-in timers on whatever computer you're working on, maybe using some interrupts or something like that. And we'll get into that later. But for now, what this will do is just make it so that there's a little bit of a delay, a few milliseconds before we actually process the joystick and before we actually move the sprite. And that's really it there. So let's go ahead and take a look at the actual code running. All right, so here we are on my actual physical C256. I have already loaded the code into memory, so let's go ahead and start it. So there it is, there's my little ship, and now I've got a joystick wired in. Obviously you can't see that, but I've got it in here, and as I move the joystick around, you can see that my ship moves around pretty smoothly and pretty quickly, a lot better than in the previous example. And so there you have it. This is just again, just a little quick one today, and we'll work on some more stuff for another tutorial. Thanks for watching, and I hope this was useful to you.